For centuries, astronomers looked at Mars and saw mystery written in rust. It is the one place in the universe other than Earth where we have projected our deepest hopes and our darkest fears. We looked at those red sands and imagined canals, civilizations, and invading armies. We dreamed of a neighbor, a second Earth hidden just beyond the darkness of space. But when we finally landed our machines on the surface, the dream turned into haunting reality. We didn't find cities, we didn't find any forests, we found a graveyard. It is a place of absolute desolation, a frozen desert where the silence has remained unbroken for billions of years. However, the tragedy of Mars is not that it has always been a dead world. The tragedy is that it was once alive. The stones tell us a story of a blue world, thick with clouds and rushing water. Mars didn't just fade away, it was murdered, and the culprit is the very star that gives us life. Today, we're looking at a planetary crime scene. To understand the history of Mars, we have to stop thinking of it as a static rock and start thinking of it as a failed Earth. From a distance, the family resemblance is undeniable. Both worlds are rocky, both have polar ice caps, and both sit within the habitable zone of the Sun. But three distinct pieces of evidence, dried river valleys, ancient lake beds, and chemical isotopes, tell us that 3.7 billion years ago, the similarity was even more striking. Mars was warm, it was wet, and it had an atmosphere thick enough to support liquid water on the surface. So, how did a water world become a desert? How does an entire planet lose its atmosphere? The answer lies in a complex interplay of geology and solar physics. It is a weird story about the death of a magnetic heartbeat and the relentless violence of the solar wind. Mars died 3 billion years ago, and today we're going to find out exactly how it happened. To understand what was lost, we first have to reconstruct the victim. When we look at the Martian surface today, specifically the ancient highlands of the south, we see the scars of flowing water. These aren't just small trickles. We see branching river networks that looks exactly like the Amazon or the Nile. We see deltas where massive rivers emptied into vast craters, depositing sediment layer by layer over millions of years. This period is known as the Nokian era. During this time, the Martian atmosphere wasn't the thin wisp of carbon dioxide we see today, which is 100 times thinner than Earth's. It was likely incredibly dense, perhaps even denser than Earth's atmosphere is right now. It created a greenhouse effect strong enough to trap the heat and keep the planet warm, despite Mars being further from the Sun than we are. The Curiosity rover confirmed this when it drilled into the Gale crater, found clay minerals, rocks that can only form in the presence of neutral, life-friendly water. It tells us that for hundreds of millions of years, Mars was habitable. It was a twin of Earth, waiting for life to take hold. Some models suggest that a shallow ocean, known as Oceanus Borealis, covered nearly a third of the planet's surface. But a planet is not just a surface, it is a machine. And for the planet to keep its atmosphere, the machine inside has to keep running. Sometime around the end of the Nokian era, the engine inside Mars broke down. The tragedy began not in the sky, but deep underground. To understand why Mars died, we have to look at why Earth survives. Every second of every day, our planet is being bombarded by high-energy particles from the Sun. This is a solar wind, a stream of charged protons and electrons moving at 1,000,000 miles per hour. If this wind were allowed to hit our atmosphere directly, it would slowly strip it away, atom by atom. But it doesn't. It slams into an invisible force field called the magnetosphere. This shield is generated by a geodynamo. Deep inside Earth, a churning ocean of molten iron rotates, generating a powerful electric current that creates a magnetic field. It extends thousands of miles into space, deflecting the solar radiation around us like water around the bow of a ship. As long as the core stays hot and fluid, the shield holds. Mars once had this shield. We know this because we can still detect the ghostly remnants of the magnetism locked in the oldest rocks of the southern crust. But Mars is smaller than Earth, only about half the size. And in the laws of planetary physics, size is destiny. Because Mars is smaller, it has a higher surface area to volume ratio. It has less internal heat trapped from its formation, and it radiates the heat away into space much faster. It's the same reason a cup of coffee goes cold faster than a large soup pot. Around 4 billion years ago, the Martian core began to cool below a critical threshold. The convection currents slowed down, the churning stopped, the geodynamo shut down, and in a geological instant, the shield vanished. The planet was left naked against the cosmos. This is where the story turns from a description of geology to a tragedy. Without a magnetic field to deflect the solar wind, the energetic particles from the sun began to slam directly into the upper atmosphere of Mars. On Earth, when solar particles hit the atmosphere near the poles, they create beautiful auroras. On Mars, without a global field to guide them, they created a global catastrophe. This process is called sputtering. It's a violent game of atomic billiards. A high-speed solar particle hits an atom of atmospheric gas, oxygen, nitrogen, or carbon, and kicks it so hard that it achieves escape velocity. The atom is knocked completely off the planet and lost to space forever. It seems like a slow process. Just a few pounds of gas is lost every second. But time is deep. Over hundreds of millions of years, this relentless erosion stripped away nearly 99% of the Martian atmosphere. NASA's MAVEN mission, Mars, Atmosphere and Volatile Evolution, was sent there specifically to measure this crime scene. MAVEN found a smoking gun in the isotopes. Isotopes are versions of atoms with different weights. Lighter versions of gases are easier to blow away than heavier ones. MAVEN found the Martian atmosphere is heavily enriched with heavy isotopes of argon and carbon. This is the fingerprint of the solar wind. It tells us that the lighter air didn't just vanish, it was forcibly stripped away by the sun. As air pressure dropped, the greenhouse effect collapsed. The planet didn't just lose its air, it lost its blanket. There is evidence that Mars tried to fight back against this death. As the atmosphere thinned and the planet cooled, the crust thickened. But beneath that crust, pockets of heat still remained. This led to the formation of the Tharsis province, a massive volcanic plateau that hosts the largest volcanoes in the solar system, including Olympus Mons. During the Hesperian era, these volcanoes erupted with a violence we can barely comprehend. They spewed billions of tons of carbon dioxide and water vapor back into the sky, attempting to reinflate the collapsing atmosphere. It was a planetary desperate gasp for survival. But without the magnetic shield, the effort was doomed. The solar wind was waiting. As fast as the volcanoes could pump gas into the sky, the sun stripped it away. The equilibrium was broken. The volcanoes eventually went dormant as the internal heat finally died out completely, sealing the planet's fate. The consequences were catastrophic and irreversible. As the atmosphere thinned, the atmospheric pressure plummeted. This changed the physics of water on the surface. As pressure drops, the boiling point of water drops with it. On Mars today, the air pressure is so low that if you were to place a cup of liquid water on the surface, it would boil and freeze at the same time. The vast oceans of the Nokian area had nowhere to go. Much of the water sublimated, turning from ice directly into gas, and was then stripped away by the solar wind. The rest retreated underground, or locked itself into the polar caps. The planet entered a terminal deep freeze. The rivers stopped flowing, the lakes dried up, leaving behind toxic salts and cracked mud. The iron in the soil, exposed to the remaining oxygen and solar radiation, rusted, burning the blue marble into the red wasteland we see today. It is a fossilized world, preserved in a state of suspended animation. So when we look at Mars through our telescopes, we aren't just looking at a neighbor, we're looking at a warning. Mars teaches us that habitability is not a permanent state. It is a delicate balance of physics, geology, and magnetism. It requires a living core to protect a living surface. The reality of the twin paradox is that while Earth and Mars started as siblings, their paths diverged because of the simple mathematics of heat and size. We're still searching for signs that life might have started there before the lights went out. We are digging in the dried lake beds, looking for microbes that might have hidden in the dirt as their world died around them. But for now, Mars remains a silent testament to the power out of a star. It is a beautiful, terrible reminder that a planet can die. So is Mars a lost cause, or do you believe we can one day reignite the atmosphere and bring the water back? Join us next time as we explore more mysteries of the universe.